Greetings everyone. Today, we're diving into the cool topic of power factor. In our previous videos, we talked about the three types of power in AC circuits: active power, also known as real power, reactive power, and apparent power. Before we talk about power factor, it's a good idea to get familiar with them. Let's take a closer look at each type. Real power, or active power, is measured in watt. It is the hard-working energy that gets things done. When you switch on a light to brighten your room or plug in your gadgets, it's the real power that makes them come alive, transferring energy from the power source to your devices. Next, reactive power is measured in VAR. It is the energy that loves to play but doesn't really contribute much to the action. It bounces back and forth between the power source and your devices, but it's not helping with the task. Lastly, the apparent power measured in volt-amperes, or VA, takes into account of overall energy transferred, whether it's being useful like real power or just bouncing around like reactive power. If you enjoy the content, please don't forget to hit the like button, subscribe to the channel, and turn on the notification bell so you never miss any update. These powers can be related using the power triangle, with each of them as the side. Now, the term power factor steps in. Power factor is the ratio of real power to apparent power, and it doesn't have a measurement unit. Inside this power triangle, we have something called the power factor angle between apparent power and real power, also known as theta. The magnitude of power factor can also be calculated as cos theta. Besides, theta also represents the phase angle difference between voltage and current. The range of power factor sits between 0 and +1 when the circuit is lagging, or 0 and -1 when the circuit is leading. Consider an AC circuit with only resistive loads. The current and voltage are in syn. When we multiply them together, we get active power, where the power flows in the same direction. The phase angle, or theta, and reactive power are approximately 0, and power factor hits around 1, the unity power factor. This means all the power is used for real work. Now, if we change to inductive or capacitive loads, they're constantly charging or discharging. This creates a phase difference between the voltage and current. Multiply those two and you get a power waveform that swings between positive and negative. That's reactive power. Active power is approximately 0. On the other hand, theta is around +90° for inductive loads and -90° for capacitive loads. The power factor drops to nearly 0. So, no real work is taking place here. In these examples, it is important to note that cables do possess very minor resistance and inductance. Therefore, the scenarios we've explored to obtain power factor of 0 and 1 represent ideal conditions. However, in practical scenarios, it is quite unlikely to get the extreme power factor near 0. Most electrical equipment will have resistance, and they tend to be lagging. For example, an inductive motor with a 0.7 power factor, the phase shift will be around 45.6°. Then, an LED light with 0.9 power factor will have a phase shift of 25.8°. When we multiply the voltage and current for apparent power, we obtain a fluctuating but non-symmetrical power waveform that captures the total energy, both real and reactive, in the system. You might be wondering, why does the power factor matter in our electrical system? Well, power factor measures the effectiveness or how well the power system is doing. When power factor gets close to 1, it is considered good power factor. The system is more efficient, mostly running on active power that does the real work. But when power factor drops low, think less than 0.85, larger reactive power bounces between power source and load will increase the flowing current. This leads to more energy losses and higher voltage drop, making the system less efficient. Now, let's do some simple math to dive deeper into the power factor. Picture a single-phase induction motor with these specifications: 230 volts AC, 50 Hz frequency, real power at 180 watts, and reactive power at 160 VAR. Ready to solve the puzzle. Let's find apparent power, power factor, theta, and current. By looking at the power triangle, Pythagoras' theorem steps in to solve the apparent power, where S equals the square root of P squared plus Q squared, that's 240.8 VA. The power factor then will be the ratio of real power to apparent power, and we yield 0.75. Next comes the theta, which is the inverse cosine of 0.75, revealing 41 degrees. That tells us the current is lagging behind the voltage by the same angle. Last but not least, current can be calculated by one of the power formulas, and we will get around 1.05 amps. Let's make the concept of power factor simpler with an analogy you might have heard of, the pH scale. Here's how it breaks down. Unity power factor is like a pH of 7, perfectly neutral. Lagging power factor is like an acid, with a pH less than 7. On the other hand, leading power factor is akin to alkaline, with a pH greater than 7. From our earlier math, we've discovered that the power factor sits at 0.75, similar to weak acidic pH. Utilities company has to provide extra reactive power to the system. However, there's a boundary set to prevent an overflow of reactive power, otherwise utilities company will impose penalty for those crossing this limit. This is where power factor correction comes into place. An extra capacitor that works its leading effect can be added, balancing out the reactive power. This can bring the lagging system back in phase, ramping up the power factor. Let's say we bring in a 150 var capacitor connected to the system. This extra reactive power of a capacitor will be having negative sign indicates, leading, and overall reactive power drops to mere 10 var. As a result, the power factor perks up to around 1 and the total current drawn reduces to 0.78 amps. It's like adding some alkaline solution to the acidic liquid, neutralizing it to pH near 7. But what if we add in too much capacitance? Imagine a 250 var capacitor is used. The power factor might shoot past unity into minus 0.9, with a negative sign indicate, leading. It's like accidentally dumping in too much alkaline in the pH mix, and pH goes beyond 7. Now, the current's leading the voltage and this isn't great. The leading power factor can lead to a rise in the voltage, potentially stressing and even damaging equipment designed for lower voltage levels. Therefore, the optimum level is closest to unity power factor. So far, we played around with a fixed-size capacitor that suits smaller equipment. But in bigger factories or systems, capacitor bank of larger capacity measured in kVAr or kVAr is commonly used. Keep this in mind, a capacitor's reactive power isn't constant and is always dependent on its operating voltage. Besides, the capacitor bank comes with a range of steps, where it can dynamically step in and out, tweaking the power factor of the entire system. With this dynamic flexibility, the capacitor bank can fine-tune the system power factor based on load's ever-changing needs, ensuring it stays close to unity. That's it for today's video. I hope you have a better understanding on power factor and its relationship with the three forms of power. So, the next time you see those numbers, you'll know the concept behind these important parameters. If you find this video helpful, please remember to like, subscribe, turn on the notification bells, and share it with others. Thank you.